Okay, thank you for the introduction, and thanks to Renzo again for organizing this great conference. So I will be talking about minimal surfaces. So these are surfaces that locally minimize area. So we can generate them, for example, by a gradient flow of the area functional. So that would be mean curvature flow with fixed boundary conditions. But in this talk, we will be talking about a different way to generate, well, in this case, minimal surfaces, but in general, different types of surfaces, and that's by tracking trajectories of space curves as they move subject to some geometric motion law. So I will first briefly discuss some of the background that I just listed. Then we will talk about one way to generate such surfaces and about its properties and limitations. And specifically, I will talk about some topological limitations to make this talk more appropriate for this conference. And then I will be talking about some new ideas that we are working on. So basically, these two topics will discuss some new results from new papers that were actually published a couple of weeks ago. And then this will be something that's in works. So first, just a very general introduction. I will be talking about moving curves or moving closed space curves in just three-dimensional Euclidean space. And basically the framework that I will be discussing is just this simple description of geometric flow where it's initial value problem for the parameterization that's denoted by X here. And I will be denoting alpha, beta, and gamma, the tangential, normal, and binormal velocities, which can depend on local quantities such as curvature or torsion or some other, let's say, external forcing. So a very classical, simple example of this is the curve shortening flow, where the beta is just curvature, which I denote by kappa, and the gamma here is equal to 0. There's no binormal motion. And this famously just shrinks to point, even though it's more complicated for space curves, but it's maybe for a different talk. So now what do I mean by the trajectory surfaces? So these are just, as I said, trajectories of the flow. Here, as an example, I'm showing some simulations of three concentric vortex rings, which are sort of frog leaping, but in a more complicated way, as there's three of them. And you can see on the right the surfaces that they generate. So actually, in general, some people are studying so-called Hashimoto surfaces, which are generated by this binormal flow. They have some nice properties that people in graphics like to use, for example. In this first part of the talk, we will be talking about the specific motion law. So the velocity at each point on the curve is equal to 1 over torsion, or 1 over square root of torsion, and it's in the normal direction. And this, interestingly enough, generates a minimal surface. So just to imagine, very simple example is a helix curve, which will sort of shrink to line in finite time and thus create a helicoid surface. So as I said, this flow will create minimal surfaces. It will, of course, have a topology of some annulus with boundaries given by the initial and the final curve. But what I'm mostly interested in is trying to find some configurations when the final curve actually shrinks to point, and thus this will be solution to the plateau's problem with the initial boundary given by the initial curve. And then maybe I can skip some of the properties. Just maybe interesting to say that the full surface will be contained in convex hull of the initial curve because of the normal direction. So this is just a sort of maximal principle. And I will also skip some of these properties, but we can actually nicely bound the total area that's generated. And the bound can be actually even improved by Melnor-Farey theorem if the initial curve is not it. But what's maybe more interesting for this talk is that the length of the curve is monotonically decreasing. That's again given by the normal direction with positive velocity. But even more in this case, if the motion exists forever, the curve will definitely shrink to point. But there are some problems. So the first very simple problem that you may see is that the right-hand side of the motion law is sometimes undefined. But in this case, this is actually partially solved because the evolution equations of the torsion make it so that the torsion is increasing at all times. So if it's not vanishing at the initial point, it will stay this way throughout the motion. Then another maybe not very nice property, or for the goal that we have, is that for some specific curves, we know that the terminal time is bounded from above. So this will probably in these cases not shrink to the point. But this family, of course, is not as large. And then there are some topological limitations. So, of course, if the initial curve or the Fernandez frame of the curve is not a Seifert frame, then this cannot shrink to a disk. It cannot create a disk. But also, and that's what I will be talking about in next few slides, this flow is because of these restrictions from the first point. The flow is restricted to some subclass of curves, namely locally convex curves. In this case, they also need to have positive torsion. But let's just look at what this restriction gives us. So in next few slides, I will just like to briefly talk about one of the way how we can look at, or some tool that we can use for discussing these limitations. So in general, we would like to know what sort of equivalence classes are given by what we call non-degenerate homotopy. So that's very similar to regular homotopy that's for planar curves. But here there's another restriction that the curves during the homotopy must stay locally convex, which means that the curvature is non-zero everywhere. So in this case, there is no turning number, but we can define a similar property, which I call the tangent turning sign. So it's constructed in the following way. Consider the initial curve in R3, look at its tangent map, and then take any point from 2-sphere, which is not on the tangent line, and project it by stereographic projection into R2. And here, look at the planar curve and we define the tangent turning sign as -1 to the turning number of this curve. So this will give us two different numbers, and this actually relates to the correct number of equivalence classes that we have. That's all result from Feldman. And here, just to maybe get some more intuition behind the definition, here are two simple examples. So these are two different original curves. These are the tangent maps, so they live in S2. And in this case, as a point P, I chose 0.001, which is not on any of these two curves. And these are the stereographic projections, and in both of the cases here, the turning tangent sign is -1. So maybe just to clarify, I should say a little bit. I should say something about the point P, because it looks like just an arbitrary choice, and it may change the result, but actually it does not. So I will just really briefly like to visually show the intuition behind how to prove this. So in here we are looking at the two sphere, and this is part of the tangent map. Now, if we divide the S2 or the two sphere into connected components, which are divided by the curve, then if the point P and another point P is inside one of the connected components, then it's very easy to show that the turning number doesn't change, and thus the results stay the same. But let's look at the case where we have two different points in two different connected components, which are next to each other. And if we first look at the first stereographic projection with respect to the point P1, we get the picture on the left. And for the point P2, we get the picture on the right. So here, by the way, this white space inside is the rest of the sphere that's sort of inverted into this small space. So now we get these two curves, and so whatever is here inside can be is regular homotopic to what's in here, but these two arcs are different. But fortunately, they changed the turning number just by plus or minus 2. And a simple way to see this visually is just to add two circles with the same orientation to one of the arcs. So the curve, let's say, goes like this and this. And if you do this, we can then just use regular homotopy to get to the curve on the right. So adding these two circles change the total curvature by plus or minus 4 pi. So the turning number was changed by plus or minus 2, and the sign is the same. So just to again show what does this say, I will use the nice example from Renzo of the curve that's initially just a circle, and then by the time the t gets to 1, we'll get a sort of double cover, double circle. And in the initial curve and the final curve at time t equals 1 and t equals 0, we have different tangent turning signs. So this means that there must be some intermediate point where the curvature vanishes. And what it means for the geometric flows that we are discussing in this presentation is that if the tangent turning sign in the beginning, if is -1, then the flow cannot converge to round point, creating topological disk. So this is now the last part of the presentation, where I will show some new directions where we are looking at. So to basically go against some of the limitations that I discussed, I'm now looking at this sort of flow, which looks like a combination of curve-shortening flow and binormal flow. So these are just trajectories of these two, or the initial curve is purple, and it changes color as it moves in time. And here there is some additional parameter which we can look at as angle. And again, if we go through the geometry of the surface that's generated, we can get this sort of equation that dictates how this parameter should change in time. And here we can actually prescribe not just zero mean curvature, but any constant mean curvature. And one of the reasons why I'm interested in this sort of formulation is that it's close to some of the other things that we are studying, which I'm not including in this presentation. So in this picture, there is a simulation of bubble vortex, which is described as the vortex line plus at each point along the curve, we have the width of the bubble. And then by buoyancy, this goes up, and the width of the bubble is sort of a value that's that can be transported and moved around along the curve. So it's in this way similar to this theta parameter. And in both cases, there is a sort of double coupling between the geometry of the curve and this parameter. So yeah, that's why that's one of the reasons why I'm looking at this. And so I actually do have some more time, but I will go just very briefly through some of the properties here. So what's better about this flow is that we can actually talk about curves that are not locally convex. So for example, if it's not really here, but we can have in these examples. I don't have anyone that I wanted to discuss, but we can have examples which don't have positive torsion. So, for example, planar convex curve will just with this trivial initial configuration of the theta parameter create a convex hull, which is a trivial minima surface, and we can also with example of circle create catenoids and so on. So this is a richer way to generate the surfaces, but we also have to prescribe the initial initialization of the theta parameter. And in this case, the length changes by this equation, where of course if the theta parameter is within some bounds, or it's close to 0, we can bound it away from plus or minus pi divided by 2. Then we can again find some nice bounds for the length. So it's not included in this presentation, but I'm currently looking at some different ways to ensure this assumption for some configurations. Okay, so that's it. Thank you.
We have time for questions.
Sorry, I have a question about the torsional blow-up you've got in this flow. Is that in any way related to the fact that the Frenet frame is sort of not well defined in the limit of a vanishing helix?
Yeah.
And could you sort of get around that by using, you know, natural basis, the sort of parallel transport basis?
Yeah, that's very good question. So, in this case, I actually cannot because for example, the curve filtering flow is also in what I wrote defined by the Frenet frame vectors, but in this case, when the curvature is 0, this whole term vanishes, so we don't care about the direction of the normal. So in here, the framing is just it doesn't really matter, but in our case, the torsion is just not defined at all. It doesn't depend on the framing. Mm-hmm. Well, so if you would define some similar value that's analogical to torsion, but with different framing, then you can probably get around some of these existence problems. But then the spanning surface will probably not be minimal, or definitely not be minimal, if we would just use the same setup. So also maybe another way to answer this, in this specific flow, if you do a limit around these bad points where the curvature vanishes, it blows up on it doesn't have defined limit. So it's not a problem of the framing, it's the problem of the formulation of this motion.
Well, inflection points are independent from whatever frame you take. So it's intrinsic property. I am a little bit puzzled according. Yeah, I don't know.
Maybe I can ask a quick question. So you, with this dynamics, you had to restrict to a particular class of curves, these locally convex curves. Mm-hmm. Did you mention which class of minimal surfaces this gives you? Does this place restrictions on the properties of the minimal surface, or is that known?
Yeah, so I've thought about this a little bit, but I don't have any nice ways to clarify what surfaces we can get from this. Yeah.
And if I can have a brief follow-up. Mm-hmm. So with this construction, of course, you'll get a parameterization for the minimal surface. Does it have any nice properties?
So I don't know whether this is nice or useful, but there are some interesting features such as so in this first formulation, the curves that are given by the fixed time have some fixed global properties. So, for example, this strange integral of torsion or square root of torsion remains the same. So there are some strange, interesting facts, but I don't know whether they are useful for anything. Thank you.
I have a very basic curiosity. There are a number of very interesting results by Dockarm. I wondered if you, for example, relating turning points to winding numbers, etc., of curves, Are you aware of this?
Sorry, what was the name again?
Doccarmo. Doccarmo has a
Oh, I see.
is
Yeah,
pretty famous book on
yeah.
differential.
I think that I'm listing some of his work, but I don't think that I have any reference where he discusses non-degenerate homotopy. So I have a lot of old references from Feldman and Little, for example, but yeah, I don't know any specific thing that would be useful from the Carmo.
Okay, thanks.
Okay, well, let's thank Jiří again for a great talk.
Richard. This is Richard. I'm Richard. Okay. Never push.
Okay, well, our next talk is by Katsuyuki Nakayama from the Aichi Institute of Technology, who will tell us about an interactive topological organization of a vortex between vortical flow and bundle of vorticity lines. Please.
Okay. Okay. Thank you very much for your kind introduction. And I'd like to, and I'm grateful for Professor Ricard to giving me a chance to attend this conference. Thank you very much. Now, I'd like to have a presentation about interactive topological organization of vortex between vertical flow and a bundle of vorticity lines. So vortex or vertical region is composed of successive surplanes. Excuse me. Successive surplanes along a vertical axis, and it has been very often represented by using vorticity. That is rotation of vorticity field, and such as intense vorticity region, or a set of vorticity vector, or bundle of vorticity lines. Vorticity line is just a line which tangential vector is the vorticity vector. So in the study of vortex dynamics, vorticity or vorticity line specify primary characteristics and primary characteristics. And on the other hand, it has been observed from long term that vorticity line sometimes swirls in vertical region, and it has several types of topological features, swirling or go straight like that. So these topological features of the vorticity line may represent detailed vertical structure, or it may indicate some kind of interactive relationships between vertical flow and vorticity lines. So the present our objective is the investigation of mechanism of the topological behavior of vorticity line, and investigation of interactive relationships between vertical flow and vorticity lines, applying some physical quantity of the local topology, and introducing Galois invariant coordinate system associated with surplane, and a serial scheme or local axis geometry that specify the topology of bundle of axis line in the vertical regions. So first, we introduce some topological quantities and define a Galois invariant coordinate system associated with vertical regions. So first, local topology of a velocity field can be specified by its gradient tensor, And since it has at least one axis, that is one real eigenvalues and eigenvectors. So local flow in a plane, in the arbitrary plane that is non-parallel to Xi A, real eigenvector, can be decomposed into radial and animal components. And they are expressed by specific quadratic forms by these equations. So these eigenvalues and eigenvectors of the respective quadratic forms specify the feature of azimuthal component and radial component. So sorority is a topological quantity that is defined by the geometrical average of the eigenvalue of azimuthal component. And if sorority is positive, it indicates the azimuthal flow has uniform direction, that is soaring or vertical flow. And similarly, source T is defined by the geometrical average of the eigenvalue of the radial component. And a vertical flow symmetry is defined by the ratio of the eigenvalues, two eigenvalues of the azimuthal component. So even though sorority is the same, if vertical flow symmetry changes, the azimuthal flow feature changes, and it's and also the feature of the radial component change according to the value of vertical flow symmetry. So if symmetry is low, then the radial flow tend to have both inflow and outflow. Yeah, and applying this local topology or sorority to velocity field, it specifies a vertical region where the sorority of the velocity is positive. Then, in that case, velocity gradient tensor has one eigenvalues and complex conjugate eigenvalues, say epsilon r plus minus I phi v, that is sorority of the velocity. And its corresponding eigenvectors, Xi PL plus minus I eta PL. Then flow trajectory can be represented by this equation. It indicates that the flow swirls with the intensity of the sorority of velocity in the plane defined by Xi PL and eta PL. So third plane is defined by Xi PL and eta PL. And with swirling, it converges or diverges according to the sign or intensity of epsilon r. That's just equal to arithmetic average of eigenvalues of the radial component. And flow also proceed or converge along Xi A real eigenvectors. And now we can define a vortex space that is a gravity invariant coordinate system associated with solar plane, where also normal bases are parallel to Xi PL, eta PL, and their normal vectors. And in the vortex space, velocity gradient tensor can be expressed by invariant components by these equations. So, so velocity gradient components are expressed by eigenvalues or vorticity component parallel to Xi PL or eta PL. And also we have to specify the topology of axis line or vorticity lines. So if we apply a local topology to vorticity vector, which is specified by the gradient tensor or the vorticity vector, but it does not, it can specify the topological feature of vorticity line, but it cannot, but it is not associated with vertical region or solar plane. Then we have, excuse me. Then we have a linear transformation of the gradient tensor into that in the vortex space. And then also we define a block matrix of the gradient tensor in the vortex space associated with the solar plane. Then if we estimate swirlity or sourcety in this block matrix, it can specify swirling feature or inflow or outflow feature in the swirl plane. And the next, we formulate a vortex space, vortex stretching in the vortex space. Vorticity equation can be derived from operating rotation to the Navier-Stokes equation. And the vortex stretching can be expressed by this term, where S denotes the rate of the strain tensor. And in the vortex space, the rate of strain tensor can be expressed by these terms. And the stretching term S omega can be expressed by these equations. This is very interesting result, because rate of strain tensor is unitary matrix. But however, the effect of the vortex stretching rotates vorticity vector by this non-diagonal terms. And it is also interesting that, excuse me, the swirling feature of the velocity gradient tensor and swirling feature of the vortex stretching is just the same. It has the same value of the swirlity. However, velocity gradient tensor rotates the flow clockwise. However, vortex stretching rotates swirls vorticity vector counterclockwise in the vertical region. So now we investigate mechanisms of the topological feature of vorticity lines using some examples of the vorticity line in the homogeneous isotropic turbulence analyzed in the direct numerical simulations, where the Taylor-Reynolds number is low. And the bundle of vorticity line is identified in the core region of vortices, where the intermediate Hessian of stability of the velocity is just negative. Okay, first, this figure shows example of a vertical region represented by the contour of the stability of velocity, and one bundle of the vorticity lines passing through the core region of the vortex. And the color of the contour of the vorticity line shows the swirlity of vorticity lines. So since it's in the most part, it has red regions. So in the most part, vorticity lines swirl. And this figure shows the joint probability density function of the swirlity of vorticity line and the swirlity of velocity. So it indicates that irrespective of intensity of swirling of velocity, about half region of the vortice, half region of the vortices, vorticity line swirls. And next, we analyze the direction of the swirling of the vorticity lines. So this time indicate rotational direction of vorticity vector or vorticity line in the swirl plane, which can be specify the vorticity of vertical vorticity vector in the vortex space. So the third component in the vortex of the vortex the third component of the vorticity of a vorticity vector in the swirl plane indicates just the direction of a rotation in the swirl plane. So this figure shows that vorticity line can swirl both clockwise and counterclockwise, even though vortex stretching effect swirls counterclockwise only. It's very strange. So we clarify this mechanism. First, we localize the vortex vector in the vortex space, and then and also decomposed vortex vector into radial and azimuthal component and a normal vector, normal component to floor plan. So, and then it is noted that the rate of strain tensor in the vortex stretching swirls component almost orthogonal, counterclockwise. And then the radial component just determine the swirling direction. So this figure explains this mechanisms. This figure shows one vortex vector field in the swirl plane and the decomposed radial and azimuthal components. And this figure shows a vortex stretching effect of the radial and azimuthal component. So it indicates when radial component has completely outflow features, then it has a vortex stretching effect to swirl counterclockwise. And on the other hand, this figure shows another example of a vortex vector in a swirl plane and decomposed radial and azimuthal components, where the radial component has complete inflow. And if it has complete inflow, it has a vortex stretching effect to swirl clockwise. So this result shows that clearly that the radial component, the stretching effect of the radial component determines the swirl direction of the vortex lines. So then we may wonder how the feature of the radial component, inflow or outflow, can be determined. Yes, it is. It can be clarified by the local radial component of the vortex vectors. So when we localize the vortex component, the radial component is just given by quadratic forms of the matrix described here. And then in the vortex space, these components can be expressed by this form. So non-diagonal component becomes 0, and the diagonal component is expressed by derivative of eigenvalues of the radial azimuthal component of vertical flow with respect to normal direction to the swirl plane. So if vortex developed upward, and then this component has positive values, then the radial component of vortex vector has a complete outflow. Then it has a vortex stretching effect to swirl counterclockwise. And on the other hand, if vortex decayed upward, and then this component become negative, so the radial component of vortex vector has complete inflow and has vortex stretching effect to swirl clockwise. So the vortex line swirl according to decay or development of the swirlity of the vortex. So this figure shows two examples of two vertical regions where vertical flow swirls clockwise, and on the other hand, vortex vector swirl counterclockwise because vortex or swirling developed upward, and in this case because swirling decayed upward, and so vertical flow swirls clockwise. And this figure shows joint probability density function of the direction of swirling of vorticity line and swirlity of vorticity lines. So this JPDF, sorry, in this figure, this JPDF is given in the condition to have complete outflow and development quality of the velocity. And this figure indicate in the condition that radial component has complete inflow and swirling decays. So these two JPDF shows clearly these features. So we show that the vertical flow in the swirl plane specifies a first topology of vorticity vector and vortex stretching characteristics. So vorticity lines are just dependent on vertical flow. But however, a vertical flow has also flow normal to the swirl plane, that is axial flow. So we may wonder, is a characteristic of the axial flow arbitrary? But this figure shows just one vertical region and the vertical flow swirl clockwise in the swirl plane. And in the parallel planes, vertical flow exists, of course. But however, in here, vertical flow has a somewhat upward component. And here, in this plane, vertical flow has a component to component backward, downward. Excuse me. Downward. And if it has upward component, vorticity line is swirls clockwise, and its vertical flow has a downward component, vorticity line swirl counterclockwise. So we clarify this mechanism. We rewrite again the velocity gradient tensor in the vortex space. And then it shows that the normal component, axial flow component, the derivative of this component with respect to the direction parallel to the swirl plane is 0. So the second derivative of the normal component is just important to characteristics of the axial flow. And then in incompressible flow, where the divergence of the divergence of velocity is 0, we can derive the equation, this equation, that the rotating direction of the vorticity line in the swirl plane is just equal to minus Laplacian of the normal component. And then if in the Laplacian, the Laplacian in the swirl plane is dominant, then the Laplacian of normal component in the swirl plane specify is specified by the rotating direction of vorticity lines. So this equation shows that if vorticity line swirls clockwise, and then the Laplacian of normal component in the swirl plane is positive, so then if it has upward axial flow. And then if it has vorticity line swirl counterclockwise, so normal component has downward axial flow. So this figure shows, okay, some vertical flow in several 5 planes, and the vorticity vector in this plane, and the Laplacian of the normal component or rotational component of the vorticity lines. So it clearly shows that if it rotates clockwise, it has upward axial flow. And if vorticity lines swirl counterclockwise, so it has downward axial flow. So like this. So if vortex line rotate counterclockwise, it's a downward axial flow. So
You have just under 2 minutes.
okay. Okay, so vorticity line is has been applied to indicate intensity of rotating of a vortex, but actually it represents topological dynamics of vertical flow along the vertical region, and it can twist or clockwise or counterclockwise according to development or decay or soaring flow, and not only this, vorticity line generate axial flow. So vorticity line influence vertical flow structures. So it has, so vertical flow and vorticity line has a kind of interactive organization systems. Okay, so okay, I'm sorry, the time. We have no time. So in the conclusion, vorticity vector field is structured by vertical flow in continuous flow planes, and the vertical stretching effect, that's and vertical stretching effect, that's for the vorticity lines. And the bundle of vorticity line represent topological dynamics of vertical flow along vertical regions. And also soaring of vorticity line generate axial flow in the flow plane. So vortex may have an interactive organization system between vertical flow and vorticity lines. Okay, thank you very much for your kind attention.
Hi, thank you for an interesting talk. Can I ask a point of clarification? The measures that you introduced in your talk, do you use these to identify vortex tubes in simulations, or do you find the vortex tubes first and then just use them to analyze them? Okay, did you hear what I said? Did you understand?
I'm sorry, no,
I'll repeat. Can I ask the measures that you showed us today? Do you use these to identify the locations of vortex tubes in simulations, or do you have them already, the locations already, and then you use them to just to study the dynamics?
Yes. In this turbulence, the vertical region is analyzed, identified using sphericity of velocity field.
Okay,
Yeah.
The follow-up then is, are you sure these measures are objective? Because I mean, that could it could lead to the misidentifications of things. I mean, do you get some regions where it gives you the measure which you would think, oh, this is a vortex tube, but it isn't really?
Yeah,
that's the case.
Yes. It may not the good answer to your question, but however, there are several ways to identify vortex, because we have no unified vortex definitions. But however, in this isotropic homogeneous turbulence, identified vortices using, for example, sphericity or the second invariant of velocity gradient tensor or lambda2 definition is almost the same, because this is due to the vortex behavior in this turbulence.
Okay.
Yeah. And even though, of course, if we identify intense vorticity region, is the identified result is almost the same.
Okay, thank you.
Okay, thank you.
Any other questions? So I'll ask one quick question, which is that at least what I took from the analysis that you presented, things were mostly local analysis in particular sort of bundles of vortex lines. And I wondered whether there was also a global counterpart to the analysis that you were doing.
I couldn't understand well.
Maybe I can add what does it mean local topology?
Yeah.
You mean you're asking me or you're asking?
Yes, it applies on topological quantity, in terms of local flow. But however, by analyzing the distribution of the local topology quantities, we can analyze the global topological features like vorticity.
Okay, let's thank Katsuki again for a great talk. Okay, our final talk this evening will be from Simone Zucher, who will tell us about quantum knots and minimal surfaces.
Okay, thank you very much for the introduction. And I know, Renzo, you're tired of hearing this, but I really must thank you for giving me the opportunity to be here, really. By the way, you see that Renzo is a co-author of this work. So we'll be talking about evolution of quantum knots driven by minimal surfaces. And I'd like to start with a movie of a work of 30 years ago. So this is water, and as you saw, there are two rings, okay, you see them. They have a head-on collision, and from this collision, you see the production of small rings that travel radially, and you see all these threads and bridges, and this gives you the idea of how complex classical turbulence is in viscous fluids. For this reason, those who are interested in studying turbulence prefer to play with quantum turbulence. And here, the model underneath is the Grosspitaevsky equation. And I reproduced the head-on collision of these two perturbed rings. Of course, I have to perturb manually. The initial condition must be perturbed. Otherwise, if you have just normal rings, they will enlarge, they will slow down, and then they will fade away. In order to have the production of these small rings, you need to engineer the initial condition, I would say. So I will spend the rest of my talk trying to explain how we got here. So I will say a few words about the Grosspitaevsky equation, which you have already seen these days. I will show you some movies about the dynamics of some defects. We'll try to get some evolutionary scenarios from there. And then I will show you some topological quantities like right, twist, and so on. And then we'll link the dynamics of these vortices to minimal surfaces. So Grosspitaevsky equation, as I said, you have already seen it. This is its form. By modeling transformations, you know that you can write in terms of density of a classical fluid and velocity, which is the gradient of the phase. As I said, it's much easier to analyze turbulence in quantum context because it's localized. Vorticity is localized on the defects. We're interested in dark structures, which means that for us, the density goes to infinity and goes to 1 as you go to infinity. And so we know that if you use a spectral approach based on the fast Fourier transform, which is obviously very efficient, you need a periodic box. And if your initial condition is not periodic, you need to mirror your initial condition in all directions. And so you end up with 8 times your original degree of freedom. And this might require a lot of memory and might become a huge problem. So we had an idea just a few years ago, which was to rescale the R3 domain into -1, 1 to the third through a simple transformation. And with this idea, we can impose our initial boundary conditions at infinity without truncating the domain, basically. So the Gross-Pitayevsky equation becomes this one, and then we solve in a very efficient way by strength time splitting, and we use fourth order finite difference in space. And then, as I said, in time, we use this method, and it's splitting. So we solve we have an efficient approximation of the matrix exponential for the linear part, and then the nonlinear part is solved exactly. Just a few words about the initial condition. We know very well how to impose an initial straight vortex, which, by the way, is the only time-independent solution of the Gross-Pitayevsky equation. So if you write a new code and you want to test your code, you just put this straight vortex. And if it stays there for days, then it means that your code is good. If it moves, there's something wrong. It's not the real straight vortex. Okay. Then there is another structure, which is the vortex ring, which maintain its shape. So it's a self-preserving structure which travels at constant speed. So it becomes itself in a moving reference frame. But so we know exactly how to deal with these two simple initial conditions. The problem is if you have an arbitrary initial condition like a trefoil knot, how do you generate the initial psi? Well, one idea is, given the 3D curve, by the Biot-Savart integral, you compute the velocity field, which is time-consuming, but at least you have a velocity field. Then you integrate that to get the phase, and you have to be careful. Well, it's defined up to a constant. So you set, for instance, the phase 0 somewhere in the bulk of the domain. And then from there, you integrate, making sure to stay away from vortex defects, because then you have to end your integration either on the vortex defects or at infinity. And then we assign the density according to the fourth order Patet approximation of a straight vortex. So I show you some dynamics. This is clearly a torus knot. As you can see, there's the okay, now we start again. So we start from the torus knot. Due to the perfect symmetry of the knot, there are 9 instantaneous reconnections that produce that blue ring. And then the secondary coiled ring, because of the same symmetries, generates 9 small rings that then move. So this is one. This one is made of 3 mutually orthogonal rings. And you see, first of all, the formation of 2 rings. You see it again. Okay, 2 rings, then just 1 loop, then 2, and then 3 again. So it reminds us of a cycle. And here we started from 2 ellipses. This is more interesting because you start from unknotted and unlinked simple geometries. And for a while, you see a hopeful link. Okay, now, okay, this is the Hopf link, and then it goes back to simple geometry. This reminds us of a cycle as well. And then I think the most interesting is this one, where, well, it's very fast. I should slow it down. Where you see we start from perturbed rings, very perturbed, and you see the formation of one loop and then of a trefoil knot. Actually, it's more complicated. Simple loop, hopeful link, trefoil knot. So this is a very interesting, we call it inverse cascade, but we'll see it later. So now let's try to classify these scenarios. I didn't show you this movie, but you start from a Hopf link, and then you get a single unknotted loop, and then from there you get two single loops. So this is precisely what he showed us this morning. So it's a direct topological cascade of the Hopf link. And this is one scenario. The same scenario, we put them together, and we call it collapse. For us, collapse is when there are instantaneous reconnections, so the topology changes instantaneously. And this happens only if you have very high symmetry, which in nature, of course, you don't have, but in a numerical simulation, you can. And so, as you saw in the movie earlier, you have these perturbed rings. They enlarge as they approach each other, they slow down, and because of the perfect symmetry, they reconnect at precise points, and they give rise of these radially moving small rings. So this is an example of a topological collapse. This is the torus knot 2,9. This is another example of a collapse, because you have very high symmetry in the initial condition, and then instantaneously a small ring, the blue one, is formed. The lighter one is very coiled, but as I said, it's perfectly symmetric. So at the same time, you have the production of 9 rings, and then these rings move away. This was the 3 mutually orthogonal rings. These are 3 rings originated by self-preserving rings. So we use that idea. And this reminds, as I said earlier, it reminds us of a cycle, structural cycle, because you start from 3 loops, unknotted and unlinked, and then you have the formation of 2 loops, then a single one, which is very long, and then from there you go back to 2, and then again 3. So it's a cycle. And this one, which is again a cycle, but it is a topological cycle, because you start from 2 ellipses, and so a very simple, I mean, there are 2 planar curves, unlinked and unknotted, and from there you get for a while a Hopf link. So there's a change in topology, but then again you go back to 2 unlinked loops. And finally, this is something that maybe it's hard to see, because we usually see the inverse. And in fact, we call it inverse topological cascade, because you usually see something like this. Whereas we started from 2, as I said, very perturbed rings. And then for a while, you have the formation of a single loop, and then a Hopf link. So there's a change in topology every time, but the complexity is increasing. And actually, in the end, we get the production of a trefoil knot. So as far as we know, this is the first realization of a topologically non-trivial knot, the trefoil knot, starting from very trivial initial conditions. So we think this is one of the main results. Now, about topological quantum hydrodynamics. Well, you already seen this morning, so you know that the circulation is quantized, and the helicity is defined as the dot product between the velocity field and the vorticity field. And because vorticity is singular and on vortex lines, you get that the helicity, if you do the computation, is 0. So you have this zero helicity condition. And as the width showed us this morning, you can write helicity in this way: the summation on all vortex lines of the self-linking number times its circulation plus the summation of linking numbers. And so what I did was to take these 4 cases. I mean, I did for many other cases, but I will show you just these plots. And for instance, if you take that knot, it evolves in time, and at every time step, I go and look for the vortex center line in order to have a 3D curve, which might be smooth enough to compute at least the first and second derivative. And then I need to compute the ribbon, because you know the twist is defined only through a ribbon. Otherwise, you cannot compute it. And by doing so, I can compute right, twist, linking number, and then helicity as the summation of all of them. So what we see here, try to concentrate on the red squares, okay, whose scale is on the left. That's the length of the total length of the defects. And it's clear that and the dots that you see here, where the time is the time of reconnections. And you have over there the torus knot, the 3 rings, the 2 ellipses, and the 2 perturbed rings. A constant characteristic is that the length has a maximum at reconnection time. Plus, there's an asymmetry, and you can see that after reconnection, the length decreases very quickly. So its derivative is higher in absolute value than before reconnection. And this is it's a fact that is already known, and it's due to sound emission. So for this reason, reconnections are irreversible somehow. And then on the color plots are curvatures. Since there are many loops, you have different colors, and you can see that through reconnections, there is a jump in the curvature, obviously. Here, I know it's hard to see, but again, concentrate on the red squares because that's helicity. And as you can see, helicity is always constant and equal to 0. Of course, there are some errors here in that plot, but there are because you can think that it's somehow it's difficult to get a smooth curve to do the computation of right, twist, and so on. So that's just numerical errors due to the analysis, I would say. Now, as you can see, in the first 2 cases, the rest of the plot is made of what? Circles, which you cannot identify in that plot, represent right, and diamonds twist. You can see that they compensate perfectly for each other. For instance, I don't know which one is which, but this one, this curve is perfectly compensated by this one to give 0. And when another loop starts, the blue one, the sum is 0. So helicity is 0. The same thing happens here, where you get a compensation of all right and twist. And so, again, your sum is 0. Now, here, with the 2 ellipses, at the beginning, everything seems to go as expected. But then, if you do the summation of right and twist, it's easy for you to do by eye. You get an average of minus 0.5. And as we saw earlier this morning, if you multiply by 2 the linking number, you get -1. So if you do the summation of twist, right, and linking number to get the helicity, you end up with zero helicity. So I would, and the same is for the two perturbed rings. So I would say that the zero helicity condition is confirmed. So the width might be, quiet. That we found a confirmation of what you showed this morning, and there is a progressive decay of right, which is a signature of a relaxing. Does it work? As long as it doesn't, yeah. So as I was saying that right is going down as a signature of relaxation towards unlinked rings. Now we talk about energy. This is the way to compute energy for the Gross-Pitayevsky equation. By Madelung transformation, you can divide in 4 contributions, which are more classical because you have kinetic energy, this new guy, which is quantum, we call quantum energy, and then you have potential energy and internal or interaction energy. Now, as you can see, if the density is almost constant, this happens just outside the vortex tubes, where density reaches the value of 1 quite quickly. The last 2 parts are just a constant contribution. And so where there is a gradient of the density, kinetic and quantum energy play a bigger role. Now, what's the link between that and minimal surfaces? There on the left, we have the Hopf link, and that is the surface of minimal area, which is an isophase surface, okay? So I take all possible isophases surfaces, which are safer surfaces connecting these 2 links, these 2 vortices, and I compute their areas, and then I find the minimum of this area as a function of the value of theta. And so now if you consider neglecting a small region around the vortex where density changes very quickly, you end up with a region which we call S prime minimum, which is the part of the minimum surface where density is almost constant. Then we know that from continuity equation, if density is almost constant, then the vector, the velocity field is divergence free. And since u is the gradient of the phase, you end up having the Laplacian of the phase equal to 0. But since we're looking at isophase surfaces, this means that S prime mean, which is that part of the minimal surface where rho is almost constant, is harmonic, and therefore is critical with respect to the Dirichlet functional defined in this way. If you go and look at the Dirichlet functional where you substitute psi, you end up noticing that it's made of the 2 contributions, which are the kinetic energy and the quantum energy. The only difference with what we saw before is that this is an integral on the surface, it's not on the volume. So this is a 2D integral over a particular surface. And we call this, sorry, this is not a vector, it's a scalar, of course. And I use this mathematical symbol to identify the integral on the surface. And so this is just a plot to show you that in the 4 cases that I showed you earlier, the area, the minimal area changes, and in the first case of the torus knot, it decreases almost monotonically. For the 3 rings, there's a maximum in this minimum area when you have a very long loop, and then also there you have a maximum for a certain particular configuration And whereas here, which is an inverse topological configuration, I would say cascade, you have something that changes in time. But in any case, there's definitely a link between the minimum surface and that functional, which measures the energy, because what I reported here is in blue. Just focus on the main plots. In blue, I reported that functional, which is the sum of kinetic and quantum energy. Maximum means what? That for different surfaces, I computed that functional, and then I looked at a specific time for the maximum of that functional. So max d of psi is that maximum. Whereas in for theta, the change is between 0 and 2 pi. So you have to make a lot of computations and integrals. Okay. Whereas the other one is that the same functional, but computed on a specific isophase surface, which is the one of minimum area. And it's the red plot. And as you can see, they almost overlap everywhere, so they coincide. And this means that, indeed, the minimum surface is critical for the functional. So these are the conclusions. We ran direct numerical simulations of the GPE using a new code resolving the problem about a truncated domain. We identified 3 possible scenarios: direct cascade and collapse, structural and topological cycles, and the inverse cascade. The last one is, to us, the most important, because we showed that it's possible to generate a more complex structure, the trefoil knot, starting from very simple unknotted loops. We confirmed both the time symmetry, which was already known, and the zero helicity theorem. And then we saw this link between the dynamics of these defects and the minimum area. And these are just the references for this work. So thank you very much for being here.
Very nice. I have 2 questions. One is, in the evolutions which you have shown to us, typically, how much is the compressible kinetic energy compared to the incompressible kinetic energy? Essentially, have the vortices lost much incompressible kinetic energy into sound, or just a small fraction? The second question is, with your stretch variables, how do you conserve the energy? If you have a wave packet moving away from reconnections or whatever accelerations of the vortices, as you move away, then you become unable to compute the gradient square, which is the functional of the kinetic energy. So essentially, you're shunting away the very short length scales, correct? It is as if at infinity.
Yeah, I mean, the answer is very simple, because the integrals, all the integrals that you saw, are made on surfaces, and these surfaces are very small. They don't go up to infinity. So, I mean, I didn't need to compute the gradients and so on far away from the defects, because, as I showed you earlier, this is in principle the energy, but I didn't compute the integral, the volume integral. I computed the surface integral, because anything I needed was this, basically, this part, okay? So I could compute these gradients without any problem, because the code that we used has a very fine grid in the proximity of the origin, and so that's where all the defects lie for a long time. So that was not a problem. And to answer your first question, which, if I remember correctly, was what is the weight of the compressible energy with respect to the classical one? Well, I remember I did all these plots, but right now I mean, because the main difference is localized close to the vortex lines, where the gradients of the density is larger. So you see compressible effects. To tell you the truth, right now, I don't remember the exact numbers, and I don't have the plots here. But I don't think, I mean, the behavior, I can say that, the behavior was more or less the same. I mean, I didn't see very strange things, okay? But the relative percentage, I don't remember. But for sure it was localized around the vortex defects. And then, because I think you're interested in sound emission and these kind of things, I really didn't check that, so I have no idea. Because I didn't do any integral over the whole domain. I was concentrated only on integrate stuff, energy on the surfaces, okay?